In this topic, we like to understand the role of vacuum technology in the deposition of surface coating. That means, whenever we conduct a process of deposition, it can be CVD, PVD, it can be some spray process, it can be coating by wetting, it can be electro deposition. Now, in most of the cases, we need one controlled atmosphere or a restricted atmosphere, and by this we mean that the pressure inside the reactor or the deposition chamber has to be properly controlled, and in most of the cases it is below atmospheric. Hardly there are processes which can be conducted with above atmospheric or atmospheric within a chamber, but there are processes which can be conducted in open atmosphere. Now, here we find the role of vacuum technology. The technology means here, that means it is a technique of producing a vacuum and in a particular degree. Now, we know that 760 millimeter of mercury or 1000 millibar, that is the equivalent, that is actually we understand as atmospheric pressure. Now, depending upon the process, it can be say 760 millitorr, that is atmospheric pressure. It can be conducted in several hundred torr, it can be just 1/10 of a torr, it can be some tenths of torr, it can be even 1 into 10 to the power minus 2, minus 3 or even 10 to the power minus 4. So, these are the degree of vacuum as required by a particular process, and accordingly there must be some ways and means to achieve that vacuum in a consistent manner throughout the deposition process without any risk of failure of the vacuum system, because then the whole purpose will be lost. So, this is one important aspect of coating technology or surface coating techniques, and this vacuum technology is a part and parcel of this, though it is a peripheral support, but one of the most important support for a particular coating process. Now, here we understand that this is a lecture on production of low vacuum. That means, we can just classify low vacuum and high vacuum. The term is very relative, but from our user's point of view, we can make some broad demarcation. That means, low vacuum means maybe from 760 to 1 into 10 to the power minus 3, and this is one range. We can also have from 1 into 10 to the power minus 3 to 1 into 10 to the power minus 5, that is the torr, and something even better than 1 into 10 to the power minus 5, that means it can be 10 to the power minus 6, or it can be 1 into 10 to the power minus 7 or minus 8 or minus 9. So, these are the very special demand and requirement, but for all routine thing what I mean, those processes whatever we have discussed so far, for those we need a vacuum at least in certain cases CVD, say few tenths of torr or few hundreds of torr, that is a CVD process. However, that means during the process we have to maintain a pressure it may be few tenths of torr or few hundreds of torr. However, there must be a pre-vacuum to remove air and oxygen. So, in that case, that pre-evacuation that should be done in the order of at least 10 to the power minus 3 torr. So, for all CVD, routine CVD, this is just a pre-vacuum, pre-evacuation of the reactor before we can really start the process. Now, when it comes to a PVD process, there this cleanliness is of extreme importance, and in that case a pressure between 10 to the power minus 5 to 10 to the power minus 6 as a pre-evacuation, that is most demanding, and we cannot here compromise with this base pressure, because in that case the residual oxygen which is present in air, that can also cause some contamination of the target, particularly those transitional element target which are very reactive with atmospheric oxygen and polluting the entire chamber, which may ultimately lead to poor quality of the coating. Though the process pressure may be, say, it can be 10 to the power minus 3 torr to, say, for example, 10 into 10 to the power minus 3 torr, that is the process pressure, but evacuation to this base pressure, that is just one has to arrive, and then the process pressure can be set to any of this value by proper throttling and by incorporating gas. So, here we understand for most of the CVD process a pre-evacuation of this order is necessary, and for a sputtering, ion plating, then this all sort of evaporation process, arc evaporation process, a base pressure of this order is essential. So, now what we see, the production of low vacuum. Now, production of low vacuum, let us see exactly what is meant by reduction of pressure. Now, here we have a device which is called the pump. So, it is well known for any user the role of the pump, but in this case the role of the pump would be to reduce the pressure inside a chamber, and at the beginning of the process it should be, when we open the hood or the door, it is totally atmospheric pressure, and after loading the sample or specimen to be coated or treated, it has to be evacuated, and that can be done by this pump. That means pumping down is the process, that means getting the pressure inside the chamber reduced. Now, by this what exactly we mean, that it is actually reducing the number of gas molecules within the chamber. So, it is the role of the pump, that means at the atmospheric pressure within a given volume of the vessel, there will be certain number of molecules, and when the pump starts operating connected to that chamber, it will be just reducing the number of molecules inside the chamber, and that will be translated into reduction of pressure, and which will be measured by some pressure measuring device like a barometer, or there are certain other gauges, so which can be used for measurement and assessment of the vacuum. So, what we see here, parameters of the pump. Now, here parameters of the pump which should be a guideline for proper selection. Now, just like any device, here what is very important, that is called the pumping speed. pumping speed, that means how many liters of this residual gas can be thrown out. So, that is one of the parameter of the pump, pumping speed, liter per minute or liter per second. Then comes another important parameter, what is the operation range? Operating range, that we should be very clear about. That means, all the pumps we cannot put to the chamber which is say at atmospheric pressure. So, there must be a coupling between just not one pump. So, one will follow other, one will give some backing support. So, they will be used in series. So, that is the operating range over which it can work. Then come very important thing, that pressure at the suction sites. That means, to what pressure it can bring down, what is the level of reduction of pressure. That means, pressure at the inlet, pressure at the inlet of the pump. That means, the port, inlet port means which is connected to the chamber to be evacuated, that is called the inlet port, and we have also another called the exit or the exhaust port. So, it is the inlet pressure at the inlet. Similarly, we have to know what is the pressure it can deliver at the outlet. That means, at the exit. This point is important in that there are many pumps which cannot deliver the pressure at the exit point above atmosphere. So, in that case we need another pump which will be a backing, so that it can be coupled in series in the downstream side, and that can raise the pressure of the residual gas above atmosphere, and then that can be thrown outside. So, this is also another important parameter. So, what we can find, pumping speed, operating range, pressure at inlet and pressure at outlet. So, these are the 4 parameter at least one has to look in. And then also another thing that is also important, that whether what type of gas is it is handling, whether it is inert, whether it is reactive or whether it is corrosive, and accordingly the material of construction of the pump has to be chosen. So, this is also the gas to be handled, that has to be also enlisted, gas to be handled, gas to be handled. So, these are the parameters for the pump. Now, principle of pumping for low vacuum. Now, in this case, what is the principle? Now, we have different types of pumps. Say, in one case it is just the displacement, that means few parts in the pump, those are moving, either it can be rotary or it can be reciprocating, and there is one casing or a stator and there is one moving piston or a rotor. So, that is one form of pump, and these are we call mechanical pump. So, these are mostly recommended for achieving a low vacuum, not a very high vacuum, say maybe well within 1 into 10 to the power minus 3 torr. So, from 760 to 1 into 10 to the power minus 3 torr, it is mostly this is engaged, that is the mechanical pump which are engaged in this range. Now, principle of pumping for low vacuum, that what we mean, it is actually expansion followed by compression. expansion followed by compression. Say for example, we have one chamber which is filled with atmospheric air, and then we have to evacuate this thing. Then definitely to draw this thing with the help of a pump. That means, in this downstream side the pressure has to be below than the pressure what is prevailing here, otherwise there will be no movement. And then this pump will handle just by expansion of this gas, so that pressure inside that will fall because of the expansion. That means, we have to create a volume which is more than this volume, and thereby we can have an expansion, and later on it will follow this compression will follow this expansion. So, this expansion will be followed by compression, and during this compression what is going to happen? We have to increase the pressure above atmosphere, so that it can be thrown outside. So, this is expansion, reduction of pressure, and then by compression increase of pressure above atmosphere. So, if it is atmospheric pressure, pump will reduce in its chamber this pressure below atmosphere, and then it will be increased above atmosphere, and then it will be thrown out. So, this is the pump, and that is a vessel or a chamber which is to be evacuated. So, that is called principle of pumping for low vacuum, but there are exceptions. We can also mention that without any rotary part or a moving part, a pump also can be used for this low vacuum operation, and in the language of this vacuum technology, this low vacuum evacuation, that is also called roughing. That means, rough pumping or simply roughing. So, roughing means actually getting the pressure down within this range and not below that. So, this roughing operation we have mostly it is rotating pump, but we do have also non-rotating pump. Pumps for low vacuum. So, pumps for low vacuum that we can see here, one is piston pump, then we have rotary vane pump, we have here roots pump, and then what we have here water ring pump, and there is another Zorption pump. So, this Zorption pump that is used for adsorbing the gas molecules on the surface of a specially formulated material, and that has very high surface area compared to this volume, and thereby this material will be adsorbed on this surface either by physical adsorption or by chemisorption. So, either it is physisorption or chemisorption. By these two processes, this Zorption pump can also work, and here no part is rotating. So, these are in the domain of pump for low vacuum. Now, let us look into this piston pump. So, piston pump is just like a barrel, and here what we have? We have here one valve, and then we have this piston, and this piston also can have another valve, and this can reciprocate. Now, here what we have the vessel to be evacuated, and we can have a connection with this tubing, with this plumbing to this point. So, this is valve 1 and this is valve 2. So, this is the volume to be evacuated. Now, say this is capital V. So, this volume means volume from this chamber up to this point. So, this is the tubing for connecting to this pump. Now, what happens? This piston can move up to this point. So, that is the top dead point, and thereby what happens? That is the actually the volume of this barrel when this piston go to this top dead end, and if that volume is small v, what we find that as we move this piston in this direction, then this volume V is gradually increasing and it attains the maximum value when this piston is here. And in that case we can equate, suppose now this volume V that is at atmospheric pressure, say for example. Now, what we can do here, just by equating we can write that for the first stroke, as we take it there, so there will be a fall of pressure within this system because of the change in volume. So, what was originally V, that is now capital V plus small v, enlargement of the volume, and that is why this atmospheric pressure has to fall. So, if we have the fall of pressure, if we write it just like P1, so that should be equated by P atmosphere into V, or we can get P1 is equal to P atmosphere into V divided by capital V by plus small v. Now, this is one stroke, and we can have nth stroke. After nth stroke, we can have P atmosphere by this into to the power n. Now, this way we can go. However, one thing we have to also look in. So, to what extent we can get down with this pressure. Now, here we have to look in very important thing, that this piston during its downward movement, what happens, then this is coming. So, the whole gas which is admitted within this volume V when it was here, then as the piston comes down, this port will be closed. So, connection will be cut off, and in that case what is going to happen? Now, this is at P1 pressure, but here this pressure P1 will keep on increasing because of the change in volume, and it will be squeezed. Now, this piston cannot come to this surface. So, there is some clearance left. So, it will come up to this point. So, this is called actually the dead volume. So, Vd, that is called the dead volume, and so it can increase the pressure, it can compress the pressure up to a volume which is corresponding to Vd. So, this way it will, the pressure after the squeezing here, that will exceed the atmospheric pressure, and in that case this valve 2 will open and there will be some space for evacuation of this thing, because now the pressure is more than atmosphere. So, this will escape through this valve. However, the point what just we have mentioned here, that we can also have another equation, that means this P into Vd, that will be given by this say if it is P1 and if it is P2, then what we can see that this P1 and P2 that into V, that means what we can get, this P2 will be equal to P1 into Vd by V, and this is called the compression ratio. That means, if we have a situation where this pressure after squeezing, if we cannot increase this pressure P2, say this is the pressure. So, what we have here P1, that means here what we see, this is P2, but we can also write P1 is equal to P2 into V by Vd. So, that means this is the actually reduction of pressure, but because of the squeezing P1 will be more than P2. However, after this squeezing, what has to be done, that this P1 it has to be greater than P atmospheric pressure in order that this valve 2 will open. But if we have a pressure which corresponds to this P2, that means this P2 will be coming from this equation, that means at a particular point the residual pressure within this, that is actually Pn, but this Pn after squeezing to this volume, dead volume Vd, if it cannot attain the value more than P atmosphere, in that case there will not be any further evacuation. So, what is going to happen at this point? At this point it will be simply expansion and contraction of that volume of air. So, it will, during the movement of the piston in the upward direction, there will be expansion of the gas, and during the downward movement there will be compression of the gas, but that compressed gas does not have the required pressure for opening of the valve. So, this way we can see this limitation, and this ratio comes about this dead volume to the volume of the barrel, this V by Vd, that means this Vd by V, that is about 1/8 to 1/10, and as a result of this the pressure what can be attained in this case, it will be around, it is 760 by 8. So, or to 760 by 10. For as a general rule we can say that the pressure attainable by this piston pump will be around 100 torr. So, it cannot go beyond that. So, this is, though it is very handy, very useful pump, but we can attain a pressure about 100 torr in this case. Now, come the rotary vane pump. Now, rotary vane pump is one of the industrial pump which is used with any commercial vacuum system, and that is coupled to a CVD or a PVD coating machine or equipment, so that the necessary evacuation is possible. In fact, it is a rotor, and this rotor is kept within a housing that is called a stator, and let us have a quick look in this case. So, we have this is a casing of the pump, or that is called a rotor, and here we have this casing something like this. And inside what happens? Inside eccentrically a rotor is placed. So, this has eccentricity. So, it is the axis of the stator and this is the axis of the rotor. So, this is the eccentricity and this is moving in this direction. So, that is the RPM m. Now, here what we have two vane, rotary vane. So, through this we can have the axis, and here what we have, we can put a slot. This is one vane, and this is, it is matching with this circular arc of the stator. So, that means it is in bodily contact. Here also we do not have much clearance, so it is also virtually in contact. So, we have another vane on this side. So, what we see here, a slot is cut diametrically along one diameter, and in that slot we put two plate like vane. So, this is the thickness of the vane, and it has certain width normal to this plane of the paper, and in between what we have here a spring. So, this is the spring. So, with this what we see, that these vanes, now here what we have one intake port which is connected to the pump, and here also we have one exit port. So, this is intake and this is exit. So, this is vane A and this is vane B. Now, what we can see here, that from this point, so this whole thing, rotor is rotating continuously, and during this process what happens, this A and B, they are changing their position with respect to this intake port. Now, as this thing will rotate, what we can see, we can have a quick look here. Without going into detail of this drawing, what we can see, that this is the axis of the stator, and what we can see here, if they change their position. So, what we can see, that now it is A is here and B is on this side. So, as this B is gradually moving on this direction, A is moving and B is also moving upward. In that case, what we can show here by this hatch mark, this volume will keep on increasing. So, that is actually the volume which is directly connected with the vacuum chamber, and this volume will have the maximum capacity when these two are almost here. So, that will be the volume, maximum volume, which will be swept by these two vanes, and this will be the swept volume. So, that will be the total volume. That means, when we have such thing, so in that case, as it comes here, so that then the volume will increase, and that will be the total volume. That means, now the gas which has been evacuated and inducted by this expansion process. So, because of this expansion of this volume, the pressure will fall and there will be a stream of gas which is flowing inside, and now it is entrapped here. So, it is isolated. Now, for the moment this chamber is isolated from these two vanes, and A and B have changed their position. Now, what is going to happen further to this? What we can see further, we can have another drawing here. So, this will be the position of this impeller, and then this A will be on this side. That means, when A is here, Now, A is here and B is on this side. So, this entrapped volume has changed its position, now it is on this side. So, now what is going to happen? We have this exit port and here this volume will be squeezed and compressed gradually, and because of this we have here one valve, and this valve will open because of the squeezing action. That means, the volume which was expanded up to this, which is shown here by this hatch mark, that will be again squeezed over this surface, and then the pressure will build up in this zone, and this will be squeezed up to this point. That means, the squeezing will be done between this point of this port B. B will move on this side up to this point, B will move, and then we have this confinement through these surfaces. So, that will be the volume, and that will corresponding to a pressure which will be more than the atmospheric pressure, and there will be exit of this gas. So, this will be actually the dead volume in this case. So, further removal of this material is not possible, and this way it will keep on working, and here the pumping speed we can write, the pumping speed will be actually 2 V into N. Now, what is V? V is the volume, maximum volume of that created by this impeller, and through this volume this material will be swept, and this is equal to V, and it happens twice in one rotation. That means, once A will be actively participating in pushing the material, and in another case the when B will be doing the same job. So, it will be twice in one rotation, then that is why we write 2, and that will be 2 into V n. So, that will be the pumping speed. Now, here what happens? This is actually the dead volume. Now, if we are interested to get down to a pressure of 1 into 10 to the power minus 3 torr, then we must have a compression ratio of at least 1 into 10 to the power 5, because of the simple reason, if we have 1 into 10 to the power minus 2, that means from 760 torr we have to get down to 1 into 10 to the power minus 3 torr, and rounding of this to 1000 we can get here that this is 1 into 10 to the power, say this is 10 to the power 2. If we like to have a pressure of 1 into 10 to the power minus 2, then rounding of this to 1000 we must have a compression ratio of 1 into 10 to the power 5. That means, this volume which is available for inducting the gas, and that is the maximum volume which is available, and that is squeezed to this dead volume. So, this is actually the dead volume. So, this volume to this volume, that should be actually 1 into 10 to the power minus 5. Now, here one thing we have to also mention, that in this case we have also gas ballast. The gas ballast means, in this compression side, in this side we have to have, we can have a quick look here. That means, on this side so these are the rotor and stator, that is shown. So, on this side what we have to have, here we must have one entry for air, and the whole idea here is to that if this pump admits some moisture or some condensable gas from this vacuum chamber, then that will be also squeezed and that can undergo some kind of condensation, and during this condensation what will happen in this case, there is oil. So, this will be actually contaminated with the oil, this will contaminate the oil, because on this side we have a oil reservoir and that is used, this oil is used to not to allow any air leakage in this barrel. So, this is actually the barrel and this barrel extends normal to this plane of the paper. So, not to allow any leakage of air in the barrel, we have to have this oil, and this contamination of this oil is prevented by just putting air. So, now what we have, instead of this condensing liquid on this side, we have a mixture of air and this vapor. So, the whole idea here is that here we must have a pressure, ejecting pressure. It is actually ejecting pressure. So, this ejecting pressure must be greater than this vapor pressure of this one. That means, ejection should be done without this condensation. So, what we do in this case, we can raise the vapor pressure for condensation of this mixture, instead of, if had it been just only the water vapor, then condensation would have been earlier. So, by putting this mixture of air and the vapor, we elevate this vapor pressure. So, ejection of this mixture can be done without having any condensation of this vapor, and that is why this is air venting and that is called gas ballast. So, that is allowed at the very beginning not to have that kind of contamination problem within this pump. What we have here, a liquid ring pump. Now, this liquid ring pump that is used for handling the corrosive gas in the CVD setup. Mostly in the CVD we use this liquid ring pump, because in the byproduct of this CVD it can be a corrosive gas. And this corrosive gas cannot be just, we cannot set it free, or it can also create problem for the various parts of the pump. So, here what is used? We use a water ring pump. This is also, the principle is same. That means, if we have a relook in this figure, that means what we can see, the basic principle is that here, because of this eccentricity, we have expansion of the volume and then we have contraction of the volume. This principle is also used in water ring pump. So, here we have the casing. And then what we have? So, here what we have, one impeller and this impeller has this kind of blades, and what happens that during the movement of this impeller, which is eccentric to the stator. So, we can see this thing that in this case this impeller, what is shown by the stator, that is eccentric to the stator, and here we have this water ring. So, that means this is actually the water ring, it can be any liquid ring, and that is the border. So, what happens during this movement of this rotation, this impeller will throw this liquid, and by this centrifugal force that will be thrown towards the wall, and this will form a circle which is parallel to this axis of the stator. Now, what is going to happen in this case? There will be a gap between this rotor and this water ring. So, if we have some kind of admission point from this side and an exit point in this direction, what we can see here, that the volume is gradually changing and it is actually expanding in this side. So, there will be a fall of pressure in the CVD chamber, and followed by that what is going to happen, this material will be squeezed in this side, and then because of this squeezing action this material will be compressed and its pressure will exceed the pressure just outside and it will be thrown outside. So, it is in principle having the same practice which is used in vane pump, only the thing is that instead of a metal casing we have one water ring, and that wall is formed by this ring which is being churned and which is under circulation continuously, and because of this eccentricity we have expansion of this space and then there is a contraction of this space. So, material will be admitted from this side and then it will be delivered on this side. So, the advantage in this case is that this water ring actually protects this wall, and at the same time this liquid which is present here, that can absorb this corrosive gas, say for example TiCl4 plus CH4, that gives us TiC plus HCl, and this HCl will be well absorbed by this water and it is having this NaOH solution. So, with this it is possible to have neutralization of HCl. So, that is the way this water ring pump that is working. Now comes the Roots pump. This is also a pump which is used for handling very high quantity of liquid or high quantity of gas, and it is coupled with one of the vane pump and it can handle high volume of gas from the system. So, it is actually two double lobed impeller double lobe impeller that is used in this system, double lobe impeller. Now, how is the construction? Let us have a quick look here. And we have another one. So, it is a lobed impeller. So, this is one impeller. So, that is the axis of rotation, and the top one it looks like this. So, this is the axis of rotation, but they are not in contact and they are having 90-degree phase difference, 90-degree phase angle, and this is rotating in this direction, say this top impeller A, and B is rotating in this direction, in the opposite direction. So, these are the two impeller. Now, we can add few more feature here. Similarly, we can also add this thing. So, this is incoming and this is outgoing. So, that is the root pump, and they are driven by identical gears, so that they are in moving with the same velocity in opposite direction and with a phase angle of 90 degree. Now, what happens? This A, now this B, that this lobe, now it is here, and say this is C, and here we have A and D. Now, what is going to happen at this moment? A and B, they can change their position, and with this what may happen, that this B will come here and then D will take up this position. Now, when this D is moving on this side, then the air, this gas from this side, that will be pushed in this direction, and that will be dragged on this side, and then B is also moving in this direction, and finally, it will be that D and B, this D lobe D and this lobe B, they are going to again approach each other because of this rotation. So, when D will be here, at that point B will assume this position. So, finally, when it moves over this surface here from this, then B will be here. So, finally, what it amounts, that between this lobe and the lobe from this side, there will be some squeezing, and the gas which is admitted on this side, that will be squeezed between these two lobes when they are approaching each other, and as a result it will be squeezed and compressed on this side. So, this will be used in series with one vane pump. So, it will be just before the vane pump, and that is a part of the system to have high flow rate of the gas, and that can be evacuated at a faster rate from the vacuum system. Now, what we have seen, we have sorption pump, that means so it is actually the body of the pump that will be filled with this molecular sheet material, and here what we have, this outer casing that is filled with liquid nitrogen, and this will be connected to the chamber. So, air will be dragged and this is filled with liquid nitrogen, and this space is filled with this molecular sheave material. Molecular sheave material, some zeolite like material, alkaline. So, it is actually some alkaline metal, alumino silicate that is used, and that can absorb this all those vapors which will be condensed on those surfaces, and as a result we can have a low value of pressure inside the chamber. So, this sorption pump can be used as one of the substitute for vane pump, where we can have some limitation with this contamination with the oil. So, these are the pumps. What we can see now in the summary, that in the vacuum system we have two options, low vacuum or high vacuum, but for mostly CVD processes it is a low vacuum, and that can be well handled by this mechanical like pump like root pump, vane pump and water ring pump. So, at the very beginning this vane pump is used for pre-evacuation of the system, and when the CVD is on, it is the water ring pump that is operational, and in the process we can also use a roots pump for increasing the throughput of the system. And along with that, what we have seen that in this case air vent is also used, or gas ballast, and that is used not to allow the condensation, unwanted condensation of the vapor which is present in the evacuation chamber, and by admitting this air, this gas mixture, it raises this point the pressure under at which this condensation can take place. But at the same time, as an alternative we can have sorption pump. It can be physisorption or it can be chemisorption, and by this process also it is possible to have this rough evacuation or rough pumping, and this can be also used as a substitute for all rotary or moving mechanical pump.